Okay, if you go down there, module 2 start here. So I have included the last class period meeting, September 16th, and I'm going to start at today's meeting as soon as I can. And I also have included question and answers for chapter 3. I'm still working on it. There are too many questions. I am going to cut down into little less than what I have now. Okay. All right. I'm going to go to my PowerPoint slides and start from there where we left off on chapter 3. Use the octet rule to describe the bonding. So we gone over 2 types of bonding, ionic bonding and covalent bonding. First, we start with ionic bonding. So ionic bonding is made up of attractions between cations and anions, atoms of elements who gain or lose electrons to form ions, positively charged ions, cations, negatively charged ions, and ions. So we looked at the naming of ionic compounds. So we're going to go to where I left off last class period, mainly ionic compounds. I'm sorry, I'm going to be going over this. Covalent compound is a covalent bond. The molecules which have bonding called covalent bonds. They are formed by sharing one or more electron pairs between atoms. They are neutral species. Molecule is neutral, unlike ionic bond. The pair of bonds are shared by both atoms at the same time, and they satisfy valence shell requirements of octet valence shell for each atom. For example, if you look at hydrogen, which is a non-metal both diatomic molecule. So two electrons are shared between two hydrogen atoms. In the first, the left side of the diagram, two hydrogen atoms with one unpaired electron now in a molecule with covalent bond. This electron pair shared between two hydrogen atoms are represented by a line That's called bonding electron pairs. Shared electron pairs are called bonding electron pairs. There's a single bond between hydrogen and hydrogen. It's called a covalent bond. Between diatomic molecules, homonuclear atomic molecules like hydrogen. It's a non-polar covalent bond. So we're going to look into polarity of the covalent bond. Non-polar covalent bond is electrons are shared equally, or more or less both atoms forming the bond have similar electronegativities. The difference is less electronegativity between the two atoms making the bond. The polar covalent bond is unequal sharing. The difference in electronegativities between the two atoms are between 0.5 and 1.9. We're going to look into that. The equality of the sharing depend on the relative electronegativities of the bonded atoms. We look up in the periodic table with electronegativity values and get the number for electronegativity, and highest electronegativity subtracted, lowest electronegativity subtracted from highest electronegativity is the electronegativity difference. So that difference is used to figure out what kind of polar bonds, either non-covalent bond or polar covalent bond, are formed or not. So we can even predict, as I talked in previous slides, if electronegativity is greater than 1.9, bond is ionic. There is no sharing between two atoms. One element, metal elements, totally lose the electron, and non-metal anion is formed, gaining the total control of the electron. But we are talking about covalent bonds, non-polar covalent bonds, and polar covalent bonds. These are formed between non-metal, or non-metal, and metalloid, or two different metalloids. Non-metals and metalloids have higher electronegativities. So covalent bonds is normally formed between two non-metals with higher electronegativities. We're going to look into examples, polarity of covalent bond. We look into several bond types and calculate the electronegativity and determine what kind of a bond is formed between two elements. Sulfur, carbon and sulfur. Now, they have very close electronegativities, 2.5, 2.5. If you look in the periodic table, their values for carbon and electronegativity values for carbon and sulfur, 2.5, 2.5. Subtracted 2.5 minus 2.5 is a non-polar. If the electronegativity difference is between 0 and 0.5, we consider is a non-polar covalent bond. Ammonia has NH bonds. Nitrogen is 3.0, hydrogen is 2.9. Electronegativity difference, higher value, lower value subtracted from higher value is 0.9. 0.9 is between 0.5 and 1.9. Therefore, NH bond is considered as a polar covalent bond. OH ion, oxygen has 3.5, hydrogen has 2.1 from the periodic table. When you subtracted 2.1 from 3.5 higher value, you get 1.4. 1.4 falls between 0.5 and 1.9 range. So it's a polar covalent bond. Sodium fluoride. There are two elements, metal and non-metal. Fluoride is non-metal. Fluorine has the highest electronegativity, 4.0. Sodium has 0.9. 0.9 subtracted from 4.0, 3.1 is greater than 1.9. Therefore, greater than 1.9, definitely an ionic bond. So you can use the electronegativity as an example to figure out all kinds of bonding. In here, we are mainly focusing on now covalent bond. In a pure polar covalent bond, the more electronegative atoms attract the share of electrons more towards it, creating a partial negative charge on the higher electronegative atom. This designated by delta negative or negative, the head of a cross arrow. There's an arrow. Head of the arrow is negative. Tail of the arrow is positive. Less electronegative is losing control of the shared electron. It attracts little less. It creates a partial positive charge called delta positive of the tail of the cross arrow. So in the bottom, HCl is a covalent bond, 2.1, I forgot the chlorine, 3 something. It falls between 0.5 and 1.9. The chlorine has the highest electronegativity. The polarity is shown with a delta negative on chloride ion and delta positive, that partial positive charge, partial negative charge. So you can assign this number based on the numbers. Dipole is shown by arrow with a cross. Cross is a positive end. Arrow head is the negative end. If you look at the electron distribution in the HCl molecule, the chloride ion is in the blue, in the red. Chloride ion has more electrons. Normally, if it is non-polar, it's equally shared. The circle is encompassing both atoms, but the circle is now shifted towards the more electronegative atom, indicating more electron distribution between towards the chloride atom. Now, to describe the bonding, excuse me, bonding in covalent compounds, we use drawing called Lewis structures of molecular structure. Lewis drawing for molecular structures. To draw a Lewis structure for a particular covalent compound, you have to use, first calculate the valence electron in the molecule. Total number of valence electron. Valence electron from all the atoms making up the molecule. For a cation, you subtract 1 electron from the valence electron. For example, sodium has 1 valence electron. So cation has, sodium ion has no valence electron in the outer shell. It's lost, but it has an octet now. For an anion, add a 1 electron for each negative charge on it. So sometimes molecules are there, group of atoms like hydroxide, polyatomic ions with covalent bonds. To calculate the total number, you have to, if the charge is negative, you have to add a negative 1 electron to the total of valence electron. We're going to look into problems. Once you get the total number of valence electrons, you have to decide, excuse me, connect it to your atoms in the molecule. Normally, you can figure that out. I'm going to go through examples. For example, water. Oxygen is connected to 2 hydrogen. So that way we draw 2 bonds between oxygen and hydrogen. By connecting atoms by single bonds. Then we fill the octet or duet to hydrogen atom. Bonding electrons are single lines. Non-bonding electrons are found on an atom to itself. It's a pair of Lewis dots. Dots are used for non-bonding electrons. They are not participating in bonding between 2 atoms. The bonding electrons could be from a single bond, share of 1 pair of electrons, or double bond, sharing 2 pairs of 4 electrons total. Single bond, 2 electrons total. Triple bond is 6 electron total or 3 pairs. So there could be a single bonds, double bonds, triple bonds in a Lewis structure. Water. This is the Lewis structure. How do you get the Lewis structure? First, we get the number of valence electrons. It's calculated to be 8. How do you get the 8? Hydrogen has 1 valence electron, 2 hydrogens, 2 electrons. Oxygen has 6. 2 plus 6 is 8 valence electrons. So once you calculate the 8 electrons, valence shell, total valence shell electrons in the molecule, you connect the oxygen to hydrogen with bonds. You already use up 2 electron pairs. There are a total of 4 electron pairs, 8 divided by 2. So then try to fill octet to oxygen and duet to hydrogen. Hydrogen already have duet. Therefore, oxygen Lewis structure become as shown here. Water, in water. Nitrogen in ammonia has 5 valence electrons. Hydrogen has 1 each. 5 plus 3. 1 each make up, and hydrogen make up 3 electrons plus 5 from nitrogen, 8 electrons. So you connect the nitrogen to the bonds to the 3 hydrogens. You already use 3 electron pairs to bonding. There are a total of 4 electron pairs. 1 remaining, you put that on the nitrogen, and nitrogen has an octet of electrons, and hydrogen duet. Like that, you can calculate the total number of electron pairs, valence electron pairs in methane. Carbon has 4, hydrogen has 1 each, 4 plus 4 is 8, 8 divided by 2 is 4 pairs. So when you connect carbon to, carbon makes 4 bonds, so you have to connect with 4 bonds to hydrogen. All the electron pairs are used up. There's no non-bonding electron pairs, and you get the Lewis structure. HCl. How do you get 8 total? 7 valence electron pairs in the chlorine. Hydrogen has 1. 7 plus 1 is 8. Divided by 2 is 4 pairs. When you connect hydrogen to chlorine, there's already 1 bonding electron pair is used. Then there are 3 remaining are put on the chlorine to get the octet to it, and hydrogen has duet. So Lewis structure shows stability of a covalent molecule based on octet rule. Duet for hydrogen and octet for other atoms. Now, this molecule is called ethylene. Ethylene is used to ripen fruits. You can gas a banana in a room and get them ripen faster. Walmart does it. So the connectivity is carbon-carbon. Carbon-carbon is connected to each other. Normally in organic compounds, carbons are connected to each other. There are 2 carbons, two carbon connected by a bond. First you connect carbon to carbon with a single bond, and 4 hydrogens to each carbon, 2 hydrogens. Now you used up 5 electrons. 5 electrons is 5 bonding electron pairs. 5 bonding electron pairs is 10 electrons. There are 1 remaining electron pair. You put that in the between carbon-carbon single bond, you add another bond, it becomes double bond. So double bond is a 4 electron pair. So carbon has an octet around it, 4 bonding electron pairs on each carbon atom, hydrogen has duet. That's how he described the Lewis structure of ethylene. Acetylene is another molecule with carbon-carbon, 2 carbon atoms, have less hydrogens. It has 10 valence electrons, 4 from each carbon, 8 are 2 hydrogens, 2, 8 electron, 10 electron pairs divided by 5 electron pairs. You first connect carbon-carbon with a single bond and carbon-hydrogen with a single bond. We used up 3 electron pairs, but we have 2 more electron pairs. So 2 electron pairs are put between carbon-carbon to form a triple bond. You add 2 more, 3 electron pairs. Carbon become octet. So it satisfies the octet rule. In formaldehyde, there are 12 valence electron pairs. Carbon is 4, hydrogen is 1 from each. 2 plus 4 is 6. Oxygen has 6. 6 plus 6 become 12. 12 electrons divided by 2 is 6 pairs. First you connect carbon to hydrogens. The formula also shows carbon bonded to two hydrogen. Carbon is normally bonded to oxygen. So 4 electron pairs are used, one more left over. Then you put 2 non-bonding electron pairs on oxygen. So double bond between CO, and everybody is happy. Carbon has octet, oxygen has octet, hydrogen has duet. So that's how you get the Lewis structure. Lewis structure of carbonic acid. Carbonic acid is when carbon dioxide dissolved in water, it forms carbonic acid. So total number of valence electron pairs is 24. The connectivity is carbon is the middle atom, oxygens are then next, 3 oxygens, and then the hydrogen to the oxygen. So when you fill up octet, 2 oxygen on the OH, get 2 electron pairs, lone pairs, and then double bond is normally formed between oxygen. Oxygen makes 2 bonds, C double bond to O. All the oxygens have octet, carbon has octet, hydrogen has duet. That's how you get the Lewis structure of carbonic acid. We're going to do some practice problem about Lewis structures now. First, we need to draw hydrogen peroxide. Then we need to draw methanol and acetic acid. Normally, we have to know the connectivity. In hydrogen peroxide, 2 oxygen are bonded to each other, and 2 hydrogens, 1 hydrogen each bond to each hydrogen atom, oxygen atom. So in the methanol, carbon is bonded to 3 hydrogens, and then carbon bonded to OH. You have to kind of know. In acetic acid, CH3 is bonded to carbon and CH3 bonded to 3 hydrogen atoms. Then that carbon bonded to C on the carboxylic acid group C. That C is bonded to oxygen with a double bond and OH, then to the OH group. So I'm going to do these problems. In hydrogen peroxide, total number of valence electrons is 14. That's how I calculated. 2 hydrogens, 2 oxygen, valence electron on hydrogen 1, and oxygen is 6. 14. First, you connect the atomic connectivities on the top diagram here. Bonding electron pairs are used to connect the atoms in this way. Then you have 3 electron pairs. That means 6 electron pairs are already used up. So there are a total of 7 electron pairs. 3 electron pairs are used. 4 electron pairs remain. Then you put them on oxygen to get the octet for the oxygen and duet for the hydrogen. That's the Lewis structure of hydrogen peroxide. Methanol. total number of 14 valence electrons. It's shown up here, connectivity on the diagram here. Carbon is bonded to 3 hydrogens. Then the carbon is bonded to OH. So we already used up 1, 2, 3, 4, 5. 5 electron pairs, 7 electron pairs from 14 is the total number of electrons divided by 2 is 7. We already used up 5. 1, 2, 3, 4, 5. We have 2 more. Where we put the 2 more is remaining electron pairs are to satisfy the octet for oxygen. Oxygen doesn't have octet here. So rest of the atoms have hydrogen has duets, carbon has octet. So therefore, the Lewis structure is of methanol is this one. we talked about acetic acid. There are 24 total valence electrons when you add all the hydrogens, carbons, oxygens. So the formula itself shows, this is a condensed formula. It shows some part of bonding. Normally, chemical formula not showing any bonding features, but organic compounds normally show connectivity. Carbon bonded to carbon. So first on the left, you connect all the atoms to carbon, 3 hydrogens, 1 oxygen, and 1 OH. Then we add a double bond to that one. Normally oxygen will make a double bond. Then we have remaining 4 electron pairs. Eight is already used up for bonding. How do I get 8 bonding? 1, 2, 3, 4, 5, 6, 7, 8. There are 3 remaining electron pairs, 4 remaining electron pairs, 8 is 12 minus 8 is 4. So they are put on the oxygen here as a lone pairs. So that's how you get the Lewis structure of these molecules. There are some exceptions to Lewis rule. There are always exceptions to scientific rule, science theories, because theories are not perfect, but best we have at the moment. So we try to solve the problems, describe with a more general theory to describe all the discrepancies later. But we had to look at the exceptions. Period 2 elements, starting from sodium, lithium, beryllium, starting from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, fills up the 2s and 2p orbitals. The bonding is normally for period 2 elements, main group elements, octet rule is followed. The 4 orbitals, 2 orbitals, 1 orbital from 2s, 3 orbitals from 2p, 4 orbitals can have a maximum of 8 electrons. Then the octet rule is followed. But third period has 3s, 3p, and 3d orbitals. Therefore, complications arise. Sometimes d orbitals can get filled up. There are 10 d orbitals, 5 d orbitals with 10 more electrons each of 5 orbital in the d orbital can have 2 electrons. Therefore, 18 electrons could be accommodated in period 3. So there are, that octet rule doesn't apply directly. These 9 orbitals, one from S, 3s, 3p, 3 orbitals, 4 and 5 from 3d orbitals added up to 9, can accommodate more than 8 electrons, can more than 8, so valence shell. Sometimes we can have atoms with less than octet. Sometimes we have atoms with unpaired electrons. They violate, they violate octet rule. We're not going to talk everything. Example, phosphorus. Phosphorus normally bond to hydrogen. The phosphorus atom in the Lewis structure of pH 3 called phosphine follow the octet rule. They have octet of electron. But some compounds, like PCl5, phosphorus atom is bonded to 5 chlorine atoms. Therefore, they have 10 valence electrons, 2 from each chlorine. So it's an exception. In phosphoric acid, if you look at the Lewis structure, phosphorus in the middle, that's the Lewis structure of phosphoric acid. Has how many bonding electron pairs? 1, 2 in here. 1, 2, 3, 4, 5. There's 10 bonding electron pairs. Therefore, it also an exception. Sulfur, just like phosphine, sulfur sometimes have compounds with 8 electrons. Their d orbitals are not filled. But when you start to fill d electrons, there are 10 electrons here. This is 12 electrons in the sulfur, in sulfuric acid. 12 from 1, 2, 3, 4, 5, 6. 6 times 2 is 12 electrons. So there are exceptions that you have to keep in mind. Everything is not perfect. Now we're going to talk about more covalent bonds, compounds. Covalent compound is a compound where all bonds are covalent. So sometimes covalent compounds are also called molecular compound. Covalent molecular is formed by covalent bonds, so sometimes we call it molecular compound. How you name binary covalent compounds? Now we are going to name it. It's different from ionic bonding, naming ionic bonds. We don't use prefixes in the ionic bonds because the charges are known. Therefore, we can use the subscript in the formula based on charges. But there are no charges on binary covalent compounds. They are either non-polar covalent bonds or polar covalent bonds. There are no charges, cations and anions. Therefore, we had to use prefixes. First thing is how you write the formula of a covalent compound. You start with less electronegative atom first. For example, sulfur and oxygen. Sulfur has less oxygen electronegativity. If you look at the periodic table with electronegativity, sulfur is the first atom. We keep the general features of ionic bond. Sulfur is first atom named sulfur. Second, we use prefixes if there are two sulfurs, sulfur, trisulfur, etc. So second element is considered highly electronegative than the first element. Its name also changed to ide, just like in non-metal naming. Nitrogen oxide is that. You don't call it nitrogen monoxide. Okay, second element, if it is one, we call mono. But first element is one, we don't call it nitrogen monoxide. Common name is nitric oxide. There are common names. In sulfur, difluoride, 2,2-fluorine. Fluorine has high electronegativity. Its name is changed in the second element, fluorine to fluoride, difluoride. Since there are no charges, you have to use the prefixes. Dinitrogen oxide. There are two nitrogens. Common name is laughing gas. Dinitrogen oxide seems to make people laugh. So that's why their name came from. So we're going to look into more naming in question and answers. I am going to talk about another topic that appear in covalent bonding, what is called resonance. Resonance is inability to describe a structure with one Lewis structure. It happens sometimes molecule with double bonds. The double bond could be distributed in various places. For many molecules and ions with double bonds, single Lewis structure does not provide an accurate representation of the molecule. For example, 3 Lewis structures are needed for carbonate ion. Let me explain. Carbonate ion, when you write down the Lewis structure, there are total of 24 electrons. How do I get 24 electrons? Carbon 4, valence electron, 24. Carbon is 4, 6 times 6 is 6 times 3 is 18, 18 plus 4 is 4 times 4 plus 6, 18, 18 plus 4 is 21, 22, 18 plus 4 is 22. Carbonate ions has 2 negative charge. 22 plus 2 more electrons for the negative charge become 24 electrons. So these electrons are distributed according to this. A double bond is between one of the carbon atom in this structure. But how do you know whether we can put that double bond here or here or here? There are 3 choices. When this happens, the molecule, in real molecule, carbon-oxygen distances are shorter than single ones, but none of electron carbon-oxygen bonds are double bonds. They average out. So it's like a resonance. It fluctuates between these 3 positions. So it's indicated by distribution of double bond in different places. Double arrows are used to indicate the resonance. Carbonate ion cannot be described by one single Lewis structure. So this happens in organic chemistry later on in benzene. There are many other compounds that resonance shows delocalization of valence electrons between different atoms. So delocalization cannot be explained by single Lewis structure. The resonance is suggested by Linus Pauling in 1930s. Linus Pauling is the one who came up with electronegativities. He's the American chemist who won 4 Nobel Prizes. He's a pretty smart person. Many molecules and ions are best described by writing 2 or more Lewis structures. That's the resonance. Individual Lewis structures are called contributing structures. So they show distribution of electrons in double bonds. Double-headed arrow is used to indicate the contributing structures, this arrow. Molecule or ion in a is called the resonance hybrid. Carbonate ion has 3 resonance hybrids, various contribution of the various 3 resonance hybrids for carbonate ion. We also use curved arrow to show movement of electron in the resonance structures. Curved arrow used to show the redistribution of valence electrons in resonance structures. The tail of the arrow identifies pair of electrons whose location is changing. Head of the arrow identifies the new location of the pair of electrons. In using curved arrows, there are only 2 allowed types of electron distribution, from double to one, from a bond to an adjacent atom. It's only one between adjacent atoms. From an atom to an adjacent bond. Sulfur trioxide molecule, like carbonate ion, has 24 electrons, represented by as a resonance hybrids of 3 equivalent contributing structures. So when you look at the double arrow, curved arrow, double bond in the structure A is redistributed to double bond in the B using the curved arrows. Electron moves between second SO single bond and double bond becomes a single bond now. Then the third redistribution is double bond is redistributed to the last remaining oxygen atom, sulfur and oxygen atom here. So you use in organic chemistry sometimes these to describe movement of electrons in molecules during reactions. There are conditions for resonance. All contributing structures must have same number of valence electrons. All of them have carbonate and sulfur trioxide. All the resonance structure, contributing structures have the same valence electron. Obey the rules of covalent bonding. Octet rule and etc. 2 electron pairs valence shell of hydrogen cannot have more than 2. 8 valence shell for the second period elements. Third period elements could have 12, up to 12, 8, 10, 12. Differ only distribution of valence electron. Positions of all nuclei must be the same. Have the same number of paired and unpaired electrons. there are conditions. You cannot just draw any structure and say it's resonance. You have to meet this condition to create contributing structures. Resonance allows us to describe properties of certain molecules using several structures, contributing structures, better than one structure alone. So we come to the point that we need to discuss molecular shape. Covalent molecules, covalent compounds have definite shape. Ionic compounds have crystal structure with ions in the solids. There's a collection of ions in the ionic compound. In covalent compound, there are distinct molecular shape, distinct molecules. We can predict shape of a covalent molecule using a model which we call valence shell electron pair repulsion theory. Excuse me. We use this model to predict the molecular shape. It's based on the idea electrons in the valence shell can repel bonding and non-bonding electron pairs could be repelled to create a shape of the geometry or shape of the molecule. Valence electrons of an atom may be involved in forming single, double, triple, or they may be unshared. In considering valence shell, single, double, triple bond are equal. Therefore, they are treated as one unit. So is unshared electron. So you look at the number of unshared electrons, single number of covalent bonds, and then decide the shape of the molecule. Each of the arrangement of the electrons in bonding electron pairs and non-bonding electron pairs creates a negatively charged region in the space around the nucleus, repelling each other. That's the idea about electron pair, valence electron, shell electron pair repulsion. Because of the charges on electron repel each other, various regions of the electron density around the atom spread out so that each is as far as possible from the other. So it creates a shape for covalent molecules based on bonding and non-bonding electron pairs. Example, methane. Lewis structure of the methane has carbon in the middle, 4 hydrogens on as the terminal atoms. That's the first one, is the Lewis structure of methane. There are 4 bonding electron pairs. 4 things in space equally distributed are distributed in a tetrahedron like that. Tetrahedral angles are 109.5, perfect tetrahedron. So if you look into carbon only here, you don't look into hydrogen electron distribution around the central atom. This is the one that decides the shape of the molecule, hub of the molecule. So carbon has 4 electron pairs. So these 4 electron pairs are distributed in space equally. According to VSEPR theory, the 4 regions radiate from the carbon at an angle of 109.5. This geometry or shape is called tetrahedral. So there are similar molecules with 4 electron pairs, bonding electron pairs with no unpaired electron, always found tetrahedral shape. The angles are 109. Ammonia, similar to methane, we already gone over Lewis structure in here. There's a lone pair, it's shown up here. Lone pair repel more than have concentrated negative charge, electrons in the lone pair. Therefore, the shape, even though shape is tetrahedral for lone pair and 3 bonding electron pairs, molecule, when you look at the molecule shape, you don't see the unshared electron. Therefore, the molecular shape is normally described by the bonding electron pairs. Bonding electron pairs are arranged in a pyramidal geometry. It deviates from little from 109 because unshared electron repel the bonding electron pairs more, unshared electron pair. So they push it down to from 109 to 107. Ammonia has pyramidal geometry. Water, like ammonia, Lewis structure is shown here. There are 2 bonding electron pairs and 2 non-bonding electron pairs. They are also arranged in a tetrahedron. 2 non-bonding, 2 bonding. But shape is decided by atoms, not by lone pairs. So shape is angular. It's deviate from 109, angle between hydrogen and oxygen is not 109. There are 2 lone pairs of electrons pushing bonding electron pairs more than in ammonia. Ammonia is 107 with 1 lone pair. So then you can describe the angle very close to 109 but deviated from 109. This molecular shape is called bent. Ammonia, it's called pyramidal. Bent or angular. Sometimes we use angular. Bent is like an elbow. Its OH bond is 104.5. Formaldehyde. We looked at the Lewis structure of formaldehyde. That's here. We look at the central atom. We are not looking at in any of these cases, central atom is carbon. Central atom decide the molecular shape. For example, a wheel hub of a wheel decide the shape of the wheel. So not the rim of the wheel. So carbon is the central atom. Central atom has 2 bonding electron pairs and a single bond and a double bond. Double bond is treated as a single bond for VS EPR theory. 3 covalent bonds, bonding electron pairs. 3 electron pairs are distributed at 120. So this is planar molecule. Side view, they are only in a trigonal planar. This arrangement is called trigonal planar. Why that is deviated from 120 here? It's shorter here, 120 and 1 16, little shorter because of the double bond pushes little bit more than the single bond. Ethylene molecule. Let me see whether I finish. Ethylene molecule, C2H4, we did the Lewis structure. It has two carbon atoms connected to each other by a double bond. We look at the both bonds, both carbon atoms for the molecular shape. Molecular shape is just like in formaldehyde, 3 double bonds, 2 double bonds, and a single bond. Single bond considered a double bond, considered a single bond, 3 bonds. Therefore, trigonal planar on this side. Double bond also keep this part of the molecule in a planar arrangement. So there's each carbon atom has a trigonal planar. Whole molecule is, each carbon atom is trigonal planar, and shape of the molecule is planar because of the two double bond between carbon kept them in same plane. Acetylene, also we talked about Lewis structure. There are one bonding electron, triple bond is considered as one bonding electron pair in the VSP-EPR theory. There are two bonding electron pairs is 180. Two bonding electron pairs can be distributed only on a linear arrangement to repel each other as far apart. Two things in space is in a linear arrangement. Therefore, whole molecule has a linear arrangement. Hydrogen-carbon bond is 180. VSCPR summary. So you can look into different geometries. If it is tetrahedral, angle is close to 109.5. But when you have lone pairs in tetrahedral arrangement of bonding and non-bonding electron pairs, when you have lone pairs like in ammonia, it becomes pyramidal or bent in water. Trigonal planar arrangement is in ethylene and formaldehyde. Linear arrangement is found in carbon dioxide and water and acetylene. Linear arrangement have 180 bond angles. Trigonal planar has 120. Tetrahedral has 109. So bend and pyramidal angles are close to 109, but they are little shorter because of the lone pair repulsions are stronger, little stronger than bond pair electron repulsion, according to VS-EPR theory. So now we have gone over shapes. Molecular shape could be based on VS-EPR theory, tetrahedral, trigonal planar, linear, bend, etc. So angles also could be predicted for different atoms in the molecule, whether it's 109, 120, or 180 linear. So we're going to look more into molecular polarity. A molecule will be polar if it has polar covalent bonds. Polar bonds, covalent bonds. And also, total molecule, even though it may have polar covalent bonds, it could be non-polar if the polarities cancel each other due to the arrangement of molecule polar covalent bond in the molecule. Let's read this. Centers of partial positive and negative charges do not coincide with the result that on the region attains net partial positive charge and another attains net partial negative charge. When you add up polar covalent bonds in space, if they add up to a total polarity, then molecule is polar. Sometimes there are arrangements. The polarities are cancelled out, like in a tetrahedral arrangement or trigonal plane arrangement, highly symmetric arrangement. Even though molecule has polarity, bonds have polarity, molecule itself don't have polarity. We're going to look into the examples. For example, carbon dioxide has two polar covalent bonds. But because of the geometry, carbon dioxide is non-polar. It's in a linear arrangement. Polarities are just like forces, resultant forces. Polar opposite cancel each other in a linear arrangement. So therefore, carbon dioxide molecule is, even though it has polar covalent bond, is non-polar molecule. For example, the polarities on carbon-oxygen bond are in opposite direction on the other CO bond. Therefore, it's like a tug of war. When you pull out in a line equal forces, there's no movement. Their equal forces cancel each other. There's no polarity in the carbon dioxide molecule. So therefore, we have to look at the molecular polarity in terms of having polar covalent bonds and whether they are distributed in the space in the Lewis structure equally, canceling each other or not. Water. Water is definitely polar. Reason for it has polar covalent bonds, OH bonds, but they are distributed in space so that they don't cancel each other. Because of its geometry is a molecular, that they add up to a total. If you look at the water molecule, I'm trying to get my cursor. Oxygen has two polar covalent bond. They add up, negative charges on oxygen adds up to a stronger pole. So therefore they don't cancel because of the geometry. Water dipoles are not cancelled out. Ammonia molecules, similar to water molecule, they add up. Ammonia has more stronger polarity in the molecule, adding up all the dipoles of the NH bond. Methylene chloride and formaldehyde are also polar. Acetylene is non-polar because they are linear molecules. Whatever polarities they have on the carbon-hydrogen bonds are cancelled out. So, for example, methylene chloride is paint stripper that we use to strip paint from furniture, CH2Cl2. There's an overall adding up of chlorine, hydrogen, chlorine, polar poles towards with each other, creating a resultant polarity in the molecule. So is the formaldehyde. They don't cancel out each other. In acetylene, the last molecule, it adds up to cancel out polarity, therefore non-polar. So we finish chapter 3. You guys have any questions about chapter 3? You have to carefully go through these topics and look into problems in chapter 3 now, okay? You guys are all right? Are you guys there?
Yes, sir.
All right, I'm going to stop the class for today, and I'm going to put the Zoom meeting on the web page. You can go back if you had any questions.